Okay, Chapter 7, the quantum mechanical model of the atom. Until the start of the 20th century, scientists believed that all physical phenomena were deterministic. And what that means is the present condition of matter influences what happens next. So if you think about, a freight train traveling at 65 miles per hour, northwest. Well, we can predict what's going to happen with that train in the future, right? We could say, well, if it continues at that rate, we can predict in such and such a time it'll be this many more miles down the track, etc. But around that time, beginning of the 20th century, some physicists that you've probably heard of discovered that subatomic particles like the electron don't follow the same rules as larger objects. The present condition for things like electrons doesn't determine the future condition. So if you think about shooting an arrow, right? If you shoot the arrow in the same direction, you can predict what's going to happen with the arrow. If you shoot an electron like that, even if you shoot it exactly the same way each time, it's most likely going to end up in a different place every time. And that's kind of hard for us to get our minds around because nothing that we can actually see behaves like this. So this will be fun. The absolutely small or quantum world of the electron behaves differently than the large or macroscopic world. So things that are far too small to see behave differently than things that are large enough to see. If they are unobserved, these absolutely small particles can be in two different states at the same time. That should be disturbing. It bothers me. So an unobserved radioactive nucleus can be simultaneously emitting a particle and not emitting a particle. We don't know until we observe it. When you observe it, then that forces it into one state or the other. Electrons are incredibly small. So a single speck of dust has more electrons in it than the number of people who have ever lived on the Earth. That's a lot of electrons in a speck of dust. Crazy small. So electrons are part of this absolutely small world that behaves differently than what we can see. The behavior of the electrons determines much of the behavior of the atoms. And we can't directly observe the electrons, but we can indirectly observe them. Something as simple as shining a laser beam light on a stream of electrons will affect their behavior. That's kind of strange, isn't it? How does the electron know it's being observed? Well, it doesn't. It's not alive. So we're going to look at a thought experiment, often referred to as Schrodinger's cat. This is not an experiment that was physically carried out. No cats were harmed. This experiment is often misunderstood. The point of it is to demonstrate how quantum strangeness does not translate to the macroscopic world, how absurd the behavior of these absolutely small things is. So we're going to watch a couple YouTube videos.
This wouldn't be a YouTube channel without a cat video. So without further ado, we present Schrodinger's Cat. I'm sure you've heard some version of this famous thought experiment. You put a cat in a bunker with some unstable gunpowder that has a 50% chance of blowing up in the next minute, and a 50% chance of doing nothing. The gunpowder is Einstein's version. Schrödinger preferred poisonous gas. Or whatever. So until we look in the bunker, we don't know whether the cat is dead or alive. And when we do look, it is either dead or alive. So if we repeat the experiment enough times with enough cats and bunkers and gunpowder, we'll see that half the time, Kitty survives, and half the time, Kitty goes bye-bye. The quantum mechanical interpretation is that before we look, the cat is in a superposition. It's both dead and alive. And our act of looking forces nature's decision. So our curiosity kills the cat. But what about the cat's perspective? Well, the cat either sees the gunpowder explode or not. So inside the bunker, we actually have these two possibilities. The powder explodes and the cat sees it explode, or the powder doesn't explode and the cat doesn't see it explode. There's no option, the powder explodes and the cat doesn't see it explode. So the cat's reality becomes entangled with the outcome of the experiment. And it's our observation of the experiment that forces nature to collapse to one option or the other. But we're like the cat too. Either the cat dies and we see it dead, or the cat lives and we see it alive. So who's observing us to force nature to collapse to one reality? Or do both possibilities happen in parallel within a larger multiverse? This collapsing to one reality problem is one of the biggest unanswered questions in quantum physics. So for Kitty's sake, can I has answer, please?
So that's kind of a fun channel. They've got a lot of physics ideas presented in a fun way. And then I've got another one here.
Hello and welcome to I Don't Think That Means What You Think It Means, where we look at bits of scientific theory that have wiggled their way into popular culture and have taken on a life of their own. Today we're talking about Schrodinger's cat, a famous thought experiment devised by the Austrian physicist Erwin Schrödinger, who helped piece physics back together after Einstein and his crew blew a giant frickin' hole in it back in the early 20th century. It's hard to overstate how much of a giant crap circus the 1920s were for physicists. Until then, everything had pretty much just been good old-fashioned Newtonian physics, where you could observe objects moving and predict how they react to various forces. Then along comes all this new research into subatomic particles that shows that they don't act predictably at all. In fact, sometimes stuff seems to be two different things at once, like an electron and a beam might act like a particle sometimes and like a wave at other times. And to make things even more the more you try to observe and measure these particles, the less naturally they behave. And to say, what now? My friends, I shall now introduce you to one of the biggest mind flogs of quantum mechanics. It's called superposition. The idea that a particle can exist in all of its theoretically possible states at the same time. So Schrödinger came up with this thought experiment to help everybody understand. Say you have a cat, and you put the cat into a steel chamber for an hour with a vial of deadly gas, a Geiger counter, a hammer, and a tiny bit of something radioactive. Bear with me here. I'll say that there's a 50-50 chance that one of the radioactives is going to decay and release some radiation within that hour. If one of the atoms decays, the Geiger counter is going to trigger the hammer, shattering the vial of poisonous gas. Really, Schrödinger? This is not the best way to get people behind the idea of funding the sciences. So, there's a 50% chance that at the end of the hour, that vial has been broken and the cat is dead. And an equally good chance that the vial hasn't been broken and the cat's just kicking it, wondering what's for supper. But what's actually happening in the box? According to quantum mechanics, any one of those radioactive atoms would be in a superposition of being both decayed and not decayed at the same time. Because that's how quantum objects act. So then, that decayed atom will have both killed and not killed the cat, right? Well, that's the logical conclusion, but a cat isn't a quantum object. A cat is a big, normal thing that obeys nice, old-fashioned Newtonian laws, so it, just like every other cat in history, is either alive or dead. Schrödinger's point, at least one of them, is that the two objects are subject to two separate sets of laws that can't be reconciled. In order to know whether the atom has decayed or not, and whether the cat is dead or not, you have to open the box and see. But in quantum mechanics, the state of superposition can't be observed. So when the evil mad scientist finally opens the chamber to observe, the superposition collapses and the outcome is ensured. Today, Schrodinger's cat is often talked about as some kind of undead zombie cat, or discussed as if the cat is actually both alive and dead in the box. But Schrodinger's point wasn't to prove that you can make a cat be both alive and dead, but instead to prove that the quantum world doesn't mesh together well with the, like normal world. And alternatively, the point is that the universe is pretty frickin' weird. There are other interpretations of quantum mechanics that might resolve the paradox, but none of them are particularly easy to test. My favorite, of course, is the many worlds interpretation that states that at the end of the experiment, and at the end of every superposition, new alternate universes are created. In this case, one in which the cat is alive, and one in which the cat's dead. And to be clear, I don't like this interpretation because I think it's the most likely one. I like it because I think it's such an excellent plot device for science fiction novels. If you have any questions, and I'm sure you do, ask them in the comments below, and I'll, do my best. Also, if you have an idea for I don't think that means what you think it means, please let us know about that too.
Okay, anybody have any questions? So a cat can't be alive and dead at the same time, can it? It's not possible. My son has a great T-shirt. It's got a wanted poster on it. Wanted, dead and alive, Schrodinger's cat. Right? The point again is that electrons and other subatomic particles do not behave in the same way as regular objects. Quantum mechanics is something that I don't know if anyone can truly understand it. And so I expect that this is going to be a confusing topic that is going to be disturbing and bothersome. Here are some quotes from the scientists that worked on it. Bohr said, "Anyone who is not shocked by quantum mechanics has not understood it." Schrödinger wrote, "I don't like it, and I'm sorry I ever had anything to do with it." He was one of the guys that developed it. He didn't like it. Albert Einstein said, "God doesn't play dice with the universe." And he attempted unsuccessfully to disprove quantum mechanics until he died. He didn't like it. He wanted to prove that it was false, but he couldn't. So we're kind of stuck with it. The quantum mechanical model does explain how electrons exist and behave in atoms. It is not an absolute, this is exactly what they're doing, but it helps us to understand them, and it helps us to understand the properties of atoms that are related to the behavior of the electrons. These include why some elements are metals and others are nonmetals, why some elements gain one electron to form an anion, others gain two electrons, why some elements are really reactive and others are practically inert, and various other periodic properties of the elements.